Dear ladies and gentlemen, my name is Mikita Ilnitsky, and as a conference manager, I would like to use this message to welcome you at the EAI MobilWare 2022. As we are here opening the 11th edition of the conference, it's justified to say that over the years, MobilWare has become a high-quality event. 2022 is the third year when the conference is taking place fully online. I would like to thank every member of the committee for being a part of the conference and for your involvement with the EAI. We are preparing 12th edition of the conference, and I would like to invite you all. Please follow the updates on the website. If you're interested in getting involved with the conference through a workshop, special session, or maybe as a TPC member, please contact me at my email address below. In fact, do not hesitate to contact me with any questions, suggestions, or feedback you may have. Thank you for your attention and enjoy EAI MobilWare 2022.
Good morning, good afternoon, everyone. This is Ridong Li from Kanazawa University, the representative of General Chairs. Welcome to the EAI MobilWare 2022, the 11th International Conference on Mobile Wireless Middleware Operating Systems and Applications, Kanazawa, Japan. This conference is sponsored by EAI. I'm Ridong Li, one of the general chairs, and another two general chairs are Ming Jia and Tariq Talib. The technical program committee chairs are Xin Yu, Abdelkader Labdi, Inder Li. Here, I would like to represent general chairs to express our great thanks to organization committee. The first technical program chairs, Xin Liu from Dalian University of Technology, China, and Abdelkader Namdi, University of Lorraine, France, Inder Li, Denmark Group, China, and the publicity and social media chairs are Zheng Yu La, Dalian Maritime University, Yun Ling, Harbin Engineering University, Zheng Xinyu, Lancaster University, and the workshop chairs are Xu Jie Li, Hohai University, Yong Wang from Chongqing University of Post and Technical Communications, and the sponsor and expert chair, Xinyu Wang, Harbin Institute of Technology, and the publication chairs are Xiaojing Ding, Nanjing University of Post and Technical Communications, Xiaoqiang Ding, Changchun University of Science and Technology. Panel chairs is Lei Xinxu, China Unicom, China. The tutorial chairs is Chang Yang from Harbin Institute of Technology, and demo chairs are Nian Zhou from Shenyang Aerospace University, Dongyang Institute of Spacecraft System Engineering, Castor, China. And local arrangement chairs is Ping Koning Ran from NVIDIA, Japan. Here we would like to express our special thanks to EAI staffs. They are Redka Vasilnadis, Martin Vojatek, Vinemo Farkas, Mikita Yelnitsky. Without them, we cannot make MobilWare to be a great success. Thanks for their great efforts. For our program, we arranged a very exciting keynote from Professor Ming Jia, Harbin Institute of Technology. She will introduce how to obtain effective resource management in satellite edge computing for collaborative satellite and terrestrial systems. For our conference, we will have 4 sessions. The first session is Middleware, Wireless, and Future Networkers. Session chair are Xin Liu from Dalian University of Technology. There are 5 papers here. And for session 2, integrated satellite terrestrial information network, the session chair is Zheng Huidong from Beijing Institute of Spacecraft System Engineering. There are 7 papers here. For the session 3, integrated satellite terrestrial intelligent information processing, decision, and planning. 1. The session chair is Dan Wang from Beijing Institute of Spacecraft System Engineering. There are 7 papers. And for session 4, integrated satellite terrestrial intelligent information processing and decision planning 2. Session chair is found by Beijing Institute of Spacecraft System Engineering. There are 7 papers here also. Welcome to join those sessions. Here, we would like to announce the Best Paper Award of EI MobilWare 2022. We would like to deliver the Best Paper Award to Ken Nongsun, Ting Li, Zihao Wu, and Cong Li for the paper entitled MiddleWare-based approach for latency-sensitive service provisioning in IoT with edge and edge collaboration. We also would like to thank for many members. This is a certificate of appreciation to Mingjia as a keynote speaker. A certificate of appreciation to Xin Liu as a technical program committee chair. And a certificate of appreciation to Dan Wang as a workshop chair. And a certificate of appreciation to Zheng Huidong as a workshop chair. And a certificate of appreciation to Yingde Li as a technical program committee chair. Thanks for their great efforts to this conference. Thank you and enjoy the conference.
Dear ladies and gentlemen, this is Professor Mingjia from Harbin Institute of Technology. I'm very appreciated that we can share this topic, how to obtain effective resource management for edge computing in collaborative satellite and terrestrial system with you in EAI MobilWare International of Conference. Outline as follows. The first is the introduction, and the second is our present research work of our research group, and the third is the conclusion and future work. Okay, let's move to the first introduction part. For the related research on 6G network, it mainly includes the following aspects. Firstly, full coverage on a global scale and overall planning and management of satellites and ground or ocean nodes, so as to truly to achieve a coverage which at ends of the Earth, followed by the full frequency band of communication technology. On the premise of the traditional communication frequency band, X-band tethers communication millimeter wave and optical communication technology to alleviate the shortage of spectrum resources, and then apply it all to meet the general application requirements of big data or artificial intelligence. Finally, the strong security of the network is realized under the technical guarantee of physical layer security and network layer security. It can be seen that, compared with 5G technology, 6G technology has been greatly improved in all aspects. 3GPP and ITU and other international organizations have set up working groups to carry out standardization research on satellite and terrestrial integration, and are committed to the research of non-terrestrial networks. The standardization of satellite communication technology in 3GPP will lay the foundation for 6G satellite and terrestrial integration. And for different applications, as shown in the figure 3, communication resources are composed of bandwidth, power, and frequency. Communication resources drive sensing resources and computing resources. And the sensing resources are composed of user sensing, satellite sensing, ground base station sensing, and satellite ground station sensing. The sensed information includes the bandwidth, power, frequency, interference, channel, and geography location. And computing resources consist of satellite user and cloud computing center and computing resources represented by the CPU cycles. Communication resources, sensing resources, and computing resources are deeply integrated and mutually enhanced. As shown in Figure 4, the application scenario of edge computing is shown, and the edge cloud computing architecture is shown in Figure 5. Compared with traditional cloud computing offloads a computing-intensive application to cloud servers with centralized and abundant computing resources, and uses the computing resources and the cloud center to complete these tasks. Although cloud computing can significantly reduce the computing delay and energy consumption of users, the transmission delay is very long due to the generally long transmission distance between the user and the cloud server. In order to solve the problem of extended transmission time, the industry has proposed the mobile edge computing technology. And edge computing deploys edge servers between terminal devices and cloud servers to provide distributed network, control computing, and storage services. Edge computing brings the computing and storage capabilities of a cloud computing center to the edge of the network, so that tasks can be proceed close to the user, thereby reducing delay and bandwidth consumption. But for users in remote areas or disaster-stricken areas, they may not be able to access the core network. This requires the employment of MEC services through satellites. And in this traditional satellite communication network architecture, the main role of communication satellites is relay and forwarding. Figure 6 shows the traditional mobile satellite communication network architecture. In the traditional satellite communication network architecture, most of the service requests of satellite terminal users will be processed through the cloud data center on the terrestrial. With the continuous development of satellite communication technology and the continuous increase in the number of services, the number of satellite terminal equipment connected to the satellite communication network has also increased sharply, which has caused the traditional satellite communication architecture to be overwhelmed. Therefore, a new computing paradigm integrates satellite communication network and edge computing technology and deploys edge computing servers on satellites so that satellite edge computing nodes have certain service processing and service response capabilities so that they can provide timely services to user terminals, execute and respond. The satellite edge computing paradigm has become a new networking model. It can break through the limitations of the surface and realize global wireless coverage and fast communication services on a large spatial temporal scale. Therefore, It has become one of the core directions of future 6G network architecture research. Some terrestrial users can still enjoy MEC services through the satellites when they cannot access the core network. The following pictures are some Chinese and foreign satellite and terrestrial collaborative network projects. And China's Tianxuan constellation project in the upper right corner is to apply high-performance computing models on satellites to improve the satellite platform's on-orbit reconstruction and application expansion capabilities, and to help the satellite have the world's first onboard cloud-native and edge computing capabilities. For the first one, seamless coverage of global services. It can provide communication and computing services in remote or rural areas becomes a challenging task due to the lack of communication infrastructure. Due to the wide coverage of low-orbit satellites carrying MEC servers and provide user computing services anywhere on the Earth. For the second, strong resistance to natural disasters. In the event of natural disasters such as floods, earthquakes, terrestrial networks are vulnerable due to the wide coverage, high throughput, and excellent system robustness of low-orbit satellites. Low-orbit satellites carrying MEC servers can provide computing services for users in disaster-stricken areas where need emergency communications. Third, about the content caching or storage. For the explosive growth of data by caching the content in the satellite or ground station, the retransmission of the same content can be avoided, and the traffic of the system can be greatly reduced. And for the last one, the security. The privacy protection and security capabilities of user information are an advantage of MEC. For traditional cloud computing, users offload computing tasks to public remote cloud computing platforms. Since user information is processed in a highly centralized manner, the security of user information in this mode cannot be guaranteed and is vulnerable to attacks. We now offload users' information to low-orbit satellites carrying edge servers. Due to the distributed deployment, small-scale nature of MEC servers, and the low concentration of valuable information, MEC servers are much less likely to be targets of security attacks. Okay, let's share some present research of our research group. And firstly, the satellite and terrestrial collaborative network is considered to be an emerging network architecture that can adapt to various services and applications in the future world. And in recent years, LEO satellites edge computing is becoming an emerging research hotspot, and MEC servers are deployed on LEO satellites to provide on-orbit computing for users around the world. Firstly, we studied the computing offloading of multi-user and multi-server under the LEO edge computing satellite, and proposed a joint optimization task offloading and communication computing resource allocation algorithm. It's called JTO-CCRO. And the idea of JTO-CCRO decouple the problem into two sub-problems of task of offloading and resource allocation, and reduce system overhead through the mutual iteration of the two subproblems. For the task of loading subproblem, a Nash equilibrium solution is obtained by the potential game theory to obtain the offloading strategy. For resource allocation subproblem, the optimal bandwidth and computing resources can be obtained by Lagrangian multiplier method. Among them, Di represents the data size of the task, Ci represents the number of the computing cycles required to complete the task, and Ti max represents the maximum tolerable delay of the task. Users can choose local computing or offload the task to edge computing satellites. And the goal of utility function of the system is the less weighted sum of time delay and energy consumption. And the resource allocation can be represented by bandwidth resource allocation and computing resource allocation. And the potential function can be expressed as follows. There are three cases. To satisfy all offloading decision changes is a strict potential gain problem. There is a Nash equilibrium solution. And decouple the original problem into task offloading and resource allocation subproblems. The system utility function is reduced by mutual iteration of these two subproblems. And the proposed GTO-CCRO algorithm has low complexity. The specific algorithm description is shown in this table. First, all users initialize local communications, and each slot T will first record the offload policy, bandwidth, and the computation resource allocation results for the current slot. Next, it iterate through all users and get a better policy for users according to definition 4. Randomly selecting an offload server from a set of better policies reduced the system utility function. According to the current offloading mode and bandwidth and the computing resource allocation formula, the bandwidth and the computing resource allocation results can be obtained, and the iteration of the current time slot is completed. In each subsequent slot, all users update the offloading decisions, bandwidth, and computation resource allocation results until the set of better policies is empty. Finally, according to the last computation slot, the final computation offload decision, bandwidth, and computation allocation results are obtained. In order to verify the feasibility of the algorithm, we first verify 6 users and 2 satellite users as servers. It can be seen from Figure 9 that the proposed algorithm can converge quickly, and after several iterations, the algorithm converges to the Nash equilibrium point. All tasks will eventually reach a constant equilibrium state. It can be seen from Figure 10 that after several iterations, the utility function of each task will converge. Our optimization goal is to minimize the system utilization function. And in order to verify the effectiveness and of this proposed algorithm, a new simulation scenario is set as k equals to 8 and n equals to 3. And the proposed algorithm in this subsection is compared with GTO, AVER, random OPT, and round OPT, and the results are shown in Figure 11. And the proposed algorithm jointly consider the impact of computing offloading and resource optimization on system performance. It can be seen from Figure 11 that the proposed algorithm is optimal, followed by GTO ever. When the user adapts the round OPT method, neither the communication and the computing resources of the MEC server nor the channel conditions between the user and the satellites can be considered, resulting in poor performance. But round OPT is better than random OPT because of the uncertainty of random OPT. And in order to further verify the relationship between the task and the system utility function, in the experiment simulation, the number of the tasks is increased from 3 to 18, and these tasks compete with each other for various resources in the system. And from Figure 12, we can see that the system utility function increases with the increase of tasks. In the initial stage, users will choose the MEC servers with good channel conditions and strong computing power to complete task offloading. So the increase in the initial stage is moderate. As the number of tasks increases, users will gradually occupy the capacity of the entire system, and the growth rate of the system utility function will also increase. When users exceed the system capacity, redundant users can only execute locally, so the system utility function grows fastly. Okay, let's move to next page. And unlike the previous scheme, a central edge multi-agent collaboration model is proposed, which regards LEO satellites and mobile users as edge agents. Each agent senses the available central agent-related information and transmits parameters to the GEO central agent. The central agent jointly optimizes the task offloading, communicating, and computing resources allocation to minimize system delay and energy consumption. Moreover, we propose a centralized control of network topology by embedding the SDN controller into the GEO central agent, which is convenient for network managers to manage and configure the entire network, rationally mobilize network resources, and increase the effective utilization of the collaboration network. Finally, extensive experiments show that the joint optimization algorithm has lower complexity and larger system utility function than other algorithms. And okay, this is about the typical task processing procedure. And mobile users can offload customized computing services to edge computing servers. However, the deployment location of the MEC server greatly affects QoE. It can be divided into these three categories. The first is the BSMEC, and when mobile users can access terrestrial networks, MEC servers can be deployed at the base station or AP points. This deployment category is similar to the traditional edge computing. However, This deployment category is not feasible when users are in harsh environments without terrestrial network access. And the second category is LEO-MEC. Considering the satellite has a wide coverage and is less affected by natural disasters, we can deploy MEC servers on satellites to provide computing services. In harsh environments such as deserts, deep mountains, and the sea, users can enjoy edge computing services through satellites. Compared with the first deployment category, the offloading delay will be longer. With the recent deployment of LEO satellites, the delay between users and the LEO satellites can be reduced to 10 milliseconds. The third is Gateway MEC. Another way is that we can deploy the MEC server near the gateway station. In this category, it can provide computing offloading services for all users within GEO satellite coverage. However, the delay from the user to the server is the longest compared with the above deploy category, and it can cause traffic congestion. Compared with the satellite-based cloud center, this offloading category only reduces the time consumed from the gateway to the cloud data center, which is not feasible for delay-sensitive tasks. The terrestrial network uses optical fiber for data transmission, so the deployment category of Gateway MEC can be regarded as a cloud data center. And the overall logical framework diagram of collaborative satellite and terrestrial network is shown in Figure 15, and each user and LEO satellite is regarded as edge intelligent agents. From Figures 15, it can be seen that the edge agent is composed of a hardware resource layer, a virtual resource layer, and a system layer. And the hardware resource layer is for the underlying hardware resources, and the virtualization resource layer is for virtualizing the hardware resources for the system layer to core and the system layer for the entire agent control. The user agent and the LEO satellite agent collect relevant information to the GEO satellite for undefined processing. Deploying an SDN controller on GEO satellites can centrally manage and control edge agents. Users and satellite agents virtualize hardware resources through NFV technology, so that the network functions do not depend on dedicated hardware. Edge agents regularly collect communication, computing resources, and relevant parameters to the central agent. And the specific parameter transfer is shown in Figure 16, and the virtualized computing and communication resources of edge agents collected through a multi-agent system. Computing resources allocation is mainly the allocation of LEO computing resources. After integrating the information to GEO consisting of parameters for undefined processing, the central agent joint optimize communication and computing resources to maximize the objective function. In the central agent, we can obtain the offload decision and resource allocation strategy through the CMCM algorithm. And according to the output of the algorithm executor, the SDN controller is used as a flow table between the user and the corresponding LEO satellites. And LEO satellites dynamically allocate the resources to users according to their traffic. It can be seen from Figure 17 that after several rounds of resource allocation and tasks of loading iterations, the system utility function gradually converges, which verifies the rationality of using two sub-problem iterations. In order to further verify the effectiveness of the proposed algorithm, exhaustive search and random offloading are used for comparison. It can be seen from Figure 18 that the performance of the proposed algorithm is infinitely close to the exhaustive search algorithm, far exceeding the random offloading algorithm. And Table 3 shows the running time of different algorithms. It can be seen that the time complexity of the proposed algorithm is lower than that of the exhaustive search. When the bandwidth comparison factor becomes 1, the user's access mode changes from SEFDMA to OFDMA, and the interference between carriers gradually decreases, and the utility function of the system gradually increases. And the system utility has a similar linear negative correlation with DU and a positive correlation with the parameter CU. And in order to further improve the spectrum utilization, we use non-orthogonal SEFDMA spectrum access between carriers. So there is inter-carrier interference between users. Theoretical analysis shows that as the bandwidth comparison factor increases, the inter-carrier interference decreases gradually and the system utility function increases. And the experimental simulation results are shown in Figure 19, which verifies the relationship between the bandwidth comparison factor and the system utility function. The effect of the parameters and on the utility function of the system is also verified. It can be seen from Figure 20 that the system utility has a similar linear negative correlation with the CU and a positive correlation with the parameter Q. And furthermore, we consider a LEO satellite edge computing system consisting of N users and an MEC server placed on the LEO satellite as shown in Figure 21. And we think that each user has independent computing tasks, each of which can be executed locally or offloaded to the LEO satellite, equipped with the MEC server for the computation. We denote the offloading decision as this, and as it is 1 represents user N offloads the computing task M to the MEC server on the LEO satellite for execution. And when it is 0, it represents that the user N task has been chosen to be executed locally. And about the energy consumption of user N locally execution task M is given as equal 1, and the delay for user N to process task M locally is expressed by equation 2. And the total delay for user N to process its task locally can be expressed by equation 3. And the total energy consumption of user N's task M offloading to the MEC server can be expressed by equation 4, and the transmission delay for user N to offload task M to the MEC server can be expressed as equation 5. In addition, the processing delay of the MEC server is given by equation 6, and the total delay when user N offloads computing task to the MEC server on the LEO satellite for execution can be expressed by equation 7. We define the system utility function here as the weighted sum of energy consumption and delay required by the processing task can be expressed by it, and we formulate the problem of energy consumption and delay for joint optimization tasks as the problem of minimizing the utility function of the system as equation 9. And for the mixed integer programming problem with a nonlinear objective function, we want to use deep learning methods to solve this problem. And the structure of the proposed algorithm is shown in figure 22. In general, we input computing tasks into DNNs, generate corresponding candidate offloading decisions for computing tasks through DNN, and allocate the bandwidth for each user through the derived optimal bandwidth allocation scheme. Then the utility function values of the system are calculated through the offloading decision scheme and bandwidth allocation scheme obtained. And then the offloading decisions corresponding to the optimal system utility function value are output as the optimal offloading decisions of this iteration. Finally, the optimal offloading decisions and the size of the computing task are stored in the memory for training DNN to achieve the goal of optimizing DNN. And the effect of the number of training steps on the converge of DNN is shown in figure 23. It can be seen from figure 23. As the number of training steps increases, the cost of DNN tends to zero rapidly, and DNN can achieve good convergence effect with a small number of training steps. And when we set these parameters to different values, the utility function values of the system are shown in figure 24a and b. It can be seen that as this parameter increases, the system utility function values of the system increase, which is obviously reasonable because the system utility function values are proportional to the parameters. And from figure 24, A and B, we can see that among the 4 different algorithms, our proposed algorithm obtains the optimal system utility function values. For our proposed algorithm, since we generate near optimal offloading decisions and adaptively allocate system bandwidth, we obtain optimal system utility function values, and the simulation results meet our expectations. And figure 25A and B shows the comparison of system utility function values corresponding to different offloading algorithms under different LEO satellite MEC server processing rates and the local devices processing capabilities. As shown in figure 25A, with the increase of the LEO satellite MEC server, processing rates and the system utility function values of the 4 offloading algorithm will decrease. This is because the higher processing rates of the MEC server reduced the processing time during the offloading process. and therefore the system utility function values decrease. It can be seen from figure 25 that the downward trend of the full offloading algorithm is very obvious. This is because the total processing time on the LEO satellite of the full offloading algorithm only depends on the processing rates of the LEO satellite MEC server. And as can be seen from figure 25b, the system utility function values of the three offloading algorithms increase with the local devices processing capabilities because it is the processing time required by the local devices to compute each data bit locally. And a larger T local means that the task takes more processing time to process locally. So the system utility function values of the three algorithms increase accordingly. It can be seen from figure 25 that the value of the system utility function of the full offloading algorithm do not change with the increase of the T local. This is because the system utility function values of the full offloading algorithm are independent of local devices processing capabilities. So this result is reasonably. Among the four offloading algorithms, our proposed algorithm achieves the optimal system utility function values. This is because our algorithm generates the offloading decisions with the lowest system utility functions values through the DNNS and can allocate the system bandwidth adaptively so we can obtain the optimal system utility function values. Okay, let's reach the final part. It is about the conclusion and the future work. And the collaborative satellite terrestrial network plays an important role in the future 6G mobile communication network, which can realize the global ubiquitous connection and support every centric customized services. Taking into account the multi-layer heterogeneity of the satellite terrestrial network, mobile edge computing technology can provide users with support for various data business computing services. Most of the existing satellite edge computing regards satellites as relay networks and neglects the deployment of MEC servers on satellites. A collaborative satellite and terrestrial edge computing network that deploys edge servers on LEO satellites is proposed. The collaborative satellite and terrestrial network architecture is introduced, and a central edge multi-agent collaboration model is designed. And further, an offloading algorithm based on deep learning to obtain near optimal offloading decisions and allocate bandwidth to each user through an adaptive optimal bandwidth allocation algorithm to obtain the optimal system utility function values is proposed. And for the future work, the satellite and terrestrial collaborative network has a large amount of dynamic and time-varying resources, which are difficult to optimize, and the future work is to use deep reinforced learning with good global search capabilities to solve the computation offloading problem in the multi-user, multi-satellite, and multitask scenario in the satellite and terrestrial collaborative network, and solve the bandwidth allocation problem in the complex scenario. Okay, we have reached the end of this presentation, and thank you very much for your attention. Wish you have a nice day and Happy New Year. Thank you. Goodbye.
Hello, this is Xing Ziyang. I want to introduce my work. My paper's title is Deep Reinforcement Learning Based Congress Control Mesh for SDA and NDA in Satellite Networks. My report list abstract introduction, system structure, professional evolution. Now the first one, I propose a Congress control algorithm based on deep reinforcement learning RLICNCC, which use a software-defined network controller to avoid the state information of the whole network in SDN. And RLICNCC can realize an adaptive Congress control machine, and consumers adjust the interest package according the global state of the network CWND. Introduction. Low orbit networks has the advantage of wide congress at low cost, and have become a future network development trend. It is very hard to collect global information of the entry network, and the congress control is very difficult. So I think I use RL and SDN in NDN. The main contributions FBI and PIT based on geolocation in the central network, SDN center network, and the adaptive congress control of the AI reinforcement learning. The ISO controller is designed in SDK to simulate different network states, and it has been proved by a large number of experiments that congress control can be achieved. Now, this is the system achievement. Let's look at the mouse. This is a producer. Producer can product some data, like a photo, like a video, or others. This is the SDN network, NDN inboard switch. This is the ground node. This is one of the consumer. Now, the SDN controller collects network information of all the network, like network topography, control node distribution, remaining bandwidth and check FBI and FIT. After that, all of these are environment. You can also call state. This is the reward. After that, input the assets 1 and 2 can create a decision maker. The decision maker is some action. For example, increase CWND, decrease CWND, or maintain the CWND. This is the whole system structure of my paper. So the key is to design the RL. After that, all the switch with NDN factions and and how can get all the network state? We can use LLDP. LLDP can collect all the information about switch. I get the network topology, cache distribution, remaining bandwidth, and update FBI and PIT. Now, in order to get the data at once, so I redesign FBI and PIT. You can see the table. The key is a unique key. The content is the content unique key. Cache time is the cache created time stamp position long to add to set cache note set like this. Now, in order to get the data at once, so I redesign the first one. If FBI content unit key is not null and found with longitude and altitude, now just return the content unit key. But if the if the FPI unit key is not count and found with if we found one, we can just return the content unit key. If all of them are failure, we just wait for next period, return the unit count. But all of them are failed, the predictor pull content again and update FIB and FIT. We can look at the 2D imagine. This is the senator orbit. This is the we can get. Now the main content confirm is like that. I use a multi-agent DDPG. We know DDPG plays an important part in RL. So this time I use many DDPG like the picture. This is one of them is DDPG. So I think I need more than one. Look at the mouse. This is the state. This is the action. This is the policy, and all of them create a value evaluation. The evaluation will update again and again. So the value evaluation will update the policy like this, do and do again and again. Now the key is the actions. I just said we have three actions. One of them is increase. Increase is just plus LAV. the first increase is two LEV. Now decrease is minor than LEV, 1.75 and 1.71 like this. The third method is mating. So the policy can do everything about the value evaluation and update the state action like this do and do more and more, so it can solve. Now the key reward function is this. This is the common function, so I think everyone will read. And now its meaning. Now the key now the key online learning congress is that input network telephone, output none. So randomly individual actor and created of each agent. After that, for period one is do that plus a and from now. Now go to the value. Now for t is a period do that. Each agent select an action with a create period n that. Now execute action and do a new observation n. Random select some date from D. For each agent, the set training critical network. After that, after the agent, we create training actor network. For each agent, update target actor network and target critical network. End for. This is the this is the main the main learning congress. Now the professional evolution. My computer is i5 with 6. Processor is 32G memory. Controller RVU. Analysis Wireshark. Traffic simulation is Mahi. Now the first one is summary test. The third authority. Now there are 66 metric. Now if the metric is not none and the metric is do compare with each other, if the same one do nothing, otherwise do 1 or 3 and enter 4. Now the first one is CDF and buffer are correct. The first picture is CDF. CDF we can say my paper RLICNCC plays very good. That DPCC. Now the other one buffered accuracy rate. This one we can also say RL. My paper RLICNCC also plays a good evolution. Now the others we can see is not. Now the second the PIT size of PIT and content time delivery rate. Now we can see that at the first time DPCCP is higher than my paper, but after time is fall, my paper plays a good value. We can see the AMQ is very low. Now we can also say the professional that. Now the blue Now the blue is my computer, and the other and the red is DPCC. This is the time. This is the rate. We can see that my paper is in blue, so it's higher than DPCC. Now this is a collusion and a framework. Now I propose to use SDN controller and bring the state information of the entry network. Now I'll slow the OP control stage, avoid control by adjusting the CWND of the console intuitive packet sending rate, redesign the PID and FIB, increasing the address. Thank you.
Hello everybody, my name is Muhammad Akra. I am happy to participate in this conference. Today I will talk about intelligent automated penetration testing using reinforcement learning to improve the efficiency and effectiveness of penetration testing. The first slide I talk to introduction. The IRS is a new type of wireless communication technology that is expected to use in the 6G era. It is a thin metasurface that can reflect electromagnetic wave in an organized manner. This technology can be used to mitigate multipath problem and is ideal for terahertz and millimeter wave communication. The increasing popularity of IRS devices has led to the development of new technologies that allow them to provide high-speed wireless communication. Some of these include this ability of perform multiple tasks at the same time, such as a power transfer and mobile edge computing. In addition, the use of millimeter wave technology has allowed for a development of unmanned aerial vehicles UAVs and smart cities. Machine learning techniques are a revolutionary technology that can be used in the development of artificial intelligence systems. They are capable of learning from vast amount of data and making predictions for the future. Due to their capabilities, various machine learning techniques have been widely adopted in the design of wireless communication systems. The various types of deep learning techniques that are commonly used, four types in IRS labeled the first type deep learning, reinforcement learning, unsupervised learning, and finally federated learning. According to the studies conducted on the use IRS, the advantage of using machine learning techniques are compared with the conventional methods. Machine learning techniques are widely used in the design of wireless communication system due to their capabilities. They can help to solve various problems related to the design of wireless communication system. A study conducted on the use of iOS assisted technology in a wireless communication system revealed the state of the art survey of the technology. The authors used microstrips paths antennas and a variety of antennas to study the operation principles of an IRS-based system. They also compared the properties of metasurface and their reflection. Therefore, this introduction, I need now know what is the problem I need to solve. The one of the most important factors that can be considered when it comes to developing an approximator is the number of features that will represent the state action space of a given attack. After there, another important factor that can be considered is the size of features set that will represent the state action space. Unfortunately, too many features can negatively affect the performance of the learning algorithm and lead to time-consuming attacks. To address this issue, they have I need now I created auto encoders that can reduce the number of features in this learning algorithm. I'm of this study. The first one, this study aims to focus on the use machine learning in the field of PT practice to make it more intelligent and efficient. It can be extended to include the use of web and application testing. A second aims the study aims to introduce the importance of machine learning in the field of PT practice. Third study, this study also describes the various steps involved in the testing and the result obtained. Now I talk to about literature review in this study. Overview of deep reinforcement learning. Deep reinforcement learning is a subfield of machine learning that uses the concepts of deep learning to provide an optimal solution for a agent experience. This process is carried out through iteration and evaluation of a reward function to determine the ideal behavior for an agent. There are three main approaches to deep reinforcement learning: the value-based approach, the policy-based approach, and the model-based approach. IRS hardware architecture and its working principles. The first one, the IRS hardware is based on a metasurface, which is a two-dimensional metamaterial. It can be used by sub-wavelength frequency range with a large number of atomic layers. And after there, this is done through the use of a large number of meta-atoms. The signal response of an IRS meta-surface atom element can be changed by designing it according to the specific requirement of the wireless communication system. After there, for instance, the size, shape, and orientation of the element can be changed to accommodate the dynamic wireless channels generated by the user mobility. Think how to testing this model. I need three types. The decision to embed RL within the practice of PT was based on its relevance and suitability. Its implementation also took into account the various decision-making problems that are involved in the process. After there, the second challenge was to choose between two models, one that model free and another that is model based. The concept of PT practice is that involves choosing a decision making task that is related to the relevant decision policy. Last one, this strategy helps minimize the number of iterations that the user has performed in order to achieve the best possible outcome. Now, the researcher tested and implemented the exact and approximated methods of solving the POMDP problem. The former method involves optimizing the value function of the model over all possible belief states, while the latter method is more computational. For most applications, exact solutions are very challenging to perform due to their complexity. The exact solution that is used for calculating the value function of POMDPS is very cost effective as it allows the user to perform the optimal action and any belief state. However, the computational power required to implement this algorithm is very high due to exponential growth of the belief space. Now I talk to result and discussions with this study. The HRL approach requires around 2 days to perform compared with the regular RLGIP going beyond the 100 machine size. HRL is more efficient and can reach 200 machine size. It performs almost as well as the Versus algorithm. In addition, HRLGIP can also be significantly faster than the previous generation. The HRLGIP effect is widely used in a large network to perform effective value optimization. It can reach a good rate in 100 machine network with over 20 clusters. The result of this study represent figure 1 and figure 2. Now I show that IAPTS outperforms both the manual and automated version of PT when it comes to solving algorithm on different lines. The authors experience as a consultant for PT also contributed to the finding. It additionally clear that IAPTS system is more cost effective than both manual and automated version of PAT. In addition, the various discount rates that were considered during the development IPTS were aimed to perceiving the realistic nature of the system. Now I see that the system IPTF the best than MSFE and PT expert, and where this a best than for multi machine this one. The second one I took the following the multiple simulation and testing. The discount rate for 0.5 was selected. We then decided to introduce some change in the algorithm to improve its performance. One of these is the use of more short-term approach to improve the performance of IAPTS system. The researchers are decided to prioritize the observation and the transition through the use of associated probabilities. The result of the evaluation process were very good, with the new GIPLP solve achieving better performance than the previous generation. In addition, the improved performance of this variant was also evidenced by the significant time saving that it made is both the PG accuracy and time consumed to further improve the performance of the program. We additionally retested the same network with or without changing the machine configuration. The results of the test were very impressive, especially when retesting the same network that was shown in figure 2. The quality of decisions that were produced by IAPTS was also beyond human expertise. In particular, when using the GIPLP solve initial beliefs algorithm, the program was able to produce decisions that were more accurate than those that were produced by a human expert. This one I typed, see that, how to retest this new retest GIP solve the same network after introducing a significant number of the to change of network configuration. This is the new system. Now how to simulation. What I know now, I see the material I used. Each performance was repeated 5 times with random seeds to ensure that the result were reproducible. The shading region on the graph represent the variability in the runs. After training the agents, we are looking at 2 indicators: the number of steps that the agents must take to reach their target and the maximum score that they can achieve. The HADRL algorithm can give an agent around 20 points depending on the scenario. It can also reduce the score by a small amount due to invalid action. It tasks to each the assists. We have tested the algorithm on various scenarios with the different action-space configuration. The performance of the IRS algorithm on different scenarios was unstable, especially when it was training with 20 and 30 hosts. It only managed to learn the optimal policy in 1 out of 4 runs. In the 50 host scenarios, the HADRL performed well as it was able to train the agent successfully. In 1 out of 4 runs, however, it was not able to get the most out of the training experience, as it took around 2,000 speed to get the agent up to seed. The IRS algorithm was able to achieve the optimal number of actions in each scenario. This is the first demonstration of how deep learning can be used in an automatic testing system to handle large action pools. Conclusion. Now, this paper presents an approach to embedding RL techniques into the cybersecurity domain. We use hierarchical RL representation to address the complexity of the PT domain. This method overcomes the scaling up challenges that were encountered in addressing large POMDBS on network with many nodes. The proposed approach involves segregating the network into small clusters and then processing the network various attacking vectors in a way that is more effective than that of certified ethical hackers. This method can be used to deal with different types of network and their complexity. The proposal IAPTF framework is a versatile and comprehensive approach that enables human experts to perform more complex tasks without requiring them to spend a lot of time. It can be several unexpected combinations that are typically ignored in manual testing. Well, thank you all. Thank you.
Hello everyone, welcome to this conference. I'm Xu from Changchun University of Science and Technology. Thank you for the kind invitation to the conference. I'm honored to have an opportunity to present our work. The topic of this paper is time slot configuration-based catching strategy for information-centric satellite network. We will present our work from the following 5 ways. Let's start with the first part. Satellite network has the features of a long communication distance, independent of geography and climate, and high mobility. They are widely applied in many ways, such as weather forecasting, resource distinction, navigation and positioning, and mobile communication. However, the high-speed motion of satellite node, inter-satellite link, interruption and reconnection, and dynamic change in network topology leave the satellite network in non-stationary state. This leads to problems such as long propagation delays, intermittent connections, and inconstant round-trip links during the data transmission. To solve the above series problem, ICN is introduced to satellite network. ICN is a new information contract network architecture that differs from the traditional IP networks to directly separating content from the location. ICN employs the content naming as a single identification for the data transmission. In network caching, technique is one of the important features in ICN. It has been proved to be an effective method to impose the positive of the content distribution. With the development of the onboard processing power, it has become a possibility to deploy the caching on satellite networks. And distributed in-network caching reduces the energy consumptions for link transmission and reduces server load. However, existing ISIN caching strategies are mostly designed for the ground networks, which can't adapt to the features of a satellite network. So there are problems such as a lake reasonable planning of the content location and the redundancy of the cached net content. So we problems the time slot caching correlations based on caching strategy for information constraint stat network in this paper. Next, the second part is introduced. The satellite network model consists of a server, the satellite network, and several users as shown in this figure. The inter-satellite link is cornerstone for interconnection and communication between the satellite node. The satellite network has a wide coverage area and provides the data transmission service to the ground users within the coverage area. The satellite nodes in the ISIN-based satellite network all have the content memory, and the content is stored and forwarded according to the caching strategy. Next, we focus on the third part of the TSCC caching strategy. Since caching the resource are scarce in the information construct satellite network, applying the traditional on-patch caching strategy causes the same content to be cached repeatedly and redundant cached net content on the transmission path. Therefore, this paper is devoted to improve the traditional cache strategy and propose TSCCS cache stage. We will present the following three areas: DSAM network model, cache node selection method, and the possibility caching theme. A snapshot are normally set as a topology diagram of the same duration, denoted as S1, S2, and Sn. By analyzing the connection of the link between the satellite nodes, it found the inter-satellite links are connected and disconnected with regularity. When the satellite network is the steady state, no link connection and no disconnection occurred between the satellite nodes, which lasted for 1 hour or more snapshot. Therefore, adjacent snapshot with the same topology are imagined under the condition that the satellite node topology is a state. Thus, the time slot is arranged as P1, P2, and PT, and the time duration of each slot is noted as TSI. The weight of each time slot is set to the WI and is expressed as the following in Q1. Local selection is one of the important indicators to measure the complete relations of the agent time slot is a connected network. The node connection in the agent time slot are opened as soon as encoding 2. On the time of the node calibration in agent time slot, the diagonal magist is abstracted present the time slot calibration as soon as the following encode 3. The DSAM network model is proposed to reflect the similarity of the connection relationships between the nodes in the time slot with the time slot calibration. In addition, a DSAM network model is shown in the following encode 4. In the satellite network, the agent vector centrality is used to find the principal centrality in the contracted super-neighborhood matrix A. The vector V contains the important values of all nodes in each time slot. The length of the vectors in each time slot is n, and this contains a total of t different time slots. Therefore, we open an n times t matrix in the following encode 6. In satellite network, the degree of importance of n nodes in each time slot and the weight of each time slot is considered to open the importance value of each node from the global perspective as WE. The selection of the catch node requires the balance between the important node with the local features and the important node with the global features in each time slot. In time slot PI, the nodes are sorted in descending order by these agent vector centrality values, and the top k important nodes with local features are selected as a catch node. At the same time, the important values of each node from the global perspective are selected in the descending order, and the top k important nodes with the global features are also selected as the catch node. Finally, 2 times k nodes are selected as the set of catch nodes for time slot PI. Since catch space of satellite is limited, the catch space of the satellite node is bound to become saturated. For as the number of the user requests increase and as the time passes, which leads to replacement catch node. To request the frequency of catched content replacement, the content with a high popularity, which is the content that has been requested by the user a lot in previous period and predict the same popularity in the future period, is scanned in the network and placed at the storage space of the catch node. Therefore, The caching possibility of content plot C at the satellite node P is obtained from the following equation 8. The ending theme based on the NS3 is selected as the simulation tools in this paper. The performance of the TSCCS caching strategy is verified by the comparing with the caching strategy of the LCE, LCD, PLW, and BTW. The LRU caching repairment strategy is adopted for the caching strategies. The average caching hit rate, average request delay, and average server load are selected as the main performance determinant in this paper. Finger survey evaluated the impacted the user request hotness on cache performance in terms of ACHR, ARD, and ASL. This experiment results in figure 3 so that the TSCS strategy is superior to other strategies. Figure 4 evaluates the impact of the node cache capacity on the cache performance in terms of ACHR, ARD, and ASL. This experiment results in figure 4, so that the TSCS strategy is superior to the other strategies. To overcome the problem of lack of reasonable length of the cache location and redundancy of the cache content in existing caching strategy in ICN. The TSCS caching strategy is proposed in this paper. By constructing the DSAM network model based on the time slot consideration, the time varying the features of the satellite network are picnicked. With the goal of selecting the cache node, the set of the cache node in each time slot is dynamically picked out based on the eigenvector centrality. Lastly, the possibility caching scheme is designed for the content with a different popularity to reduce the cache dynamic redundancy and achieve responsible placement and cache the content. Simulation experiment so that the TSCS strategy has advantage over the other teams in terms of the average cache hit rate, average request delay, and average server load. Our report is over. Thank you.
Hello everyone, I'm Zhang Dongpu. It's my honor to have the opportunity to give a presentation here. First of all, I'd like to express my sincere thanks to the committee of the workshop for giving this opportunity to our team. At the same time, I wish to share with you the recent work and progress of our team. My topic is features extraction of reconstruction model using in augmented reality system of teleoperation mobile robots.
It mainly contains 4 parts. First, I'll give a review of our challenge and then a brief introduction to the principle of the algorithm and our experiments will be shown. In the third part, I want to share with you the results and analysis of our experiments. Finally, I will summarize and look forward to the future work. Well, teleoperation robots are intelligent equipment, and they can complete scientific tasks such as long-distance petrol detection, sampling analysis, material handling under remote control. The operator monitors or controls remote robots to complete various tasks in unreachable or dangerous environments. In unfamiliar, dangerous, or inappropriate environments, it is imperative to use teleoperation robots to engage in dangerous work, such as landing on the moon, asteroids, or other unknown objects. Instead of astronauts so as to avoid human being harm during deep space exploration. For accurate teleoperation of robots, it is necessary to obtain the surface environment of the unknown object where the robot is located and judge the range and distance of its movement according to the environment. Because the unknown environment is unfamiliar and complex, the two-dimensional model is not sufficient to express the true situation of the environment, so that accurate judgment of the distance cannot be realized. In previous work, we reconstructed the three-dimensional environment model by Metashape successfully based on the 2D images collected, which lays a technical foundation for the subsequent 3D environment and models reconstructed in deep space exploration teleoperation tasks. Augmented reality is an important branch of virtual reality, which enhances the real world seen by users. It can obtain high reliability and accuracy required by remote teleoperation. If virtual environment is integrated with the real environment by combining AR systems with teleoperation robots. To solve the problems of poor accuracy and low efficiency in remote operation robots, we designed and developed an AR system for simulation control of a teleoperation mobile robot in our field work. We built an AR control platform on the remote control of robot, simulated the movement of robot in real environment, controls the tracking control commands of analog robot, and improve the remote teleoperation efficiency. With this work, we find that it is necessary to implement a real-time tracking algorithm to achieve the perfect combination of virtual and real world. Ultimately meets the requirements of man-machine collaborative operation tasks such as on-orbit AR teleoperation for unknown object environment. We have found an AR real-time tracking algorithm suitable for on-orbit teleoperation system through several frameworks. The idea of the algorithm is to implement tracking based on the reconstructed model, that is, to use the reconstructed 3D model for real-time tracking. The useful information of the prior model includes the original image used for reconstruction, the matching relationship between the 2D feather points of the reconstructed image and the 3D points of the model, and so on. Due to the usage of information related to the reconstructed 3D model,
This algorithm can effectively avoid the impact of external conditions, such as changes in lighting scenes. The steps of the real-time tracking algorithm based on the reconstruction model are shown in this page. We design and carry out relevant experiments in order to verify the algorithm. Now, let's learn about the process. The whole process of the experiment contains 7 steps, including prior reconstruction model, establish the PD tree of reconstructed model offline, input the current frame image, extract fixed points, searches 2D and 3D match points by BDF algorithm, removes mismatches by ransack algorithm, camera pose estimation. In the verification experiment of this algorithm, the target of tracking is a stone table in an open environment. The resolution of the collection image is 640 by 480. The prior data of this algorithm includes the reconstructed 3D model, the 3D point coordinates of the model, and the corresponding 2D point coordinates. All the relevant information of the reconstructed model is saved in the text file, which is used to establish the PD tree in the offline process. The reconstructed 3D model is shown in figure 2. 4 images for reconstruction are shown in figure 3. The experimental results show that 1,321 fixed feather points are extracted from the image, which takes about 5.265 seconds. For real-time tracking algorithm, the speed of extracting feather point is slow, which has 2 effects on tracking algorithm. First, more feathers can be tracked, either it is to find feather matching between images, so as to provide accurate 2D and 3D matching point pairs for camera pose estimation is follow the tracking process, which ensures the accuracy of tracking. On the other hand, the more feathers are tracked, and the slower the calculation will run because of the larger amount of data. Better parameter optimization results can be achieved via random sampling consistency algorithm. Mismatches should be removed by ransack algorithm after finding the 2D and 3D matching points. The outlier of the image should be removed, and the interior points must be retained based on this optimization result. For image matching, it is effective to use ransack algorithm to remove mismatches. The results of removing the mismatches are shown in table 1. The experimental results are shown in figure 6. Since the perspective of the current frame image is the most similar one to that of the first image among the 4 reconstructed original images, and the perspective difference between the current frame image and the last 2 images is the largest. The number of matching points with the first image is the largest, while only 1 matching point can be found with the third and the fourth image after removing the mismatches by ransack algorithm. After the mismatches removed by ransack algorithm, there are 42 2D and 3D matching points match the parent frame image and the reconstructed model. These matching points will be used as the input data for the following camera pose estimation. After searching by BBF algorithm and removing some mismatches by ransack algorithm, 42 2D and 3D corresponding points are used as the input data of camera pose estimation. LM iterative optimization algorithm is used to optimize the reprojection error function of the image and obtain the camera pose metrics of the current frame image. The initial value of the iterative algorithm is the P matrix calculated by the planliner algorithm. It takes 0.2 seconds for LM optimization of current frame image, and the reproduction error is 0.548 pixels. The final experimental results of real-time tracking algorithm based on reconstruction model in AR are shown in Figure 7. 6 images are tracked via this algorithm, and the operation time of the algorithm is shown in Table 2. As shown in Table 2, single image tracking via this algorithm will cost about 6 to 7 seconds totally on the experimental environment. And due to the low speed of 6 point extraction, it takes quite a long time to track via the real-time algorithm in the experimental system. In short, improvements of the algorithm include 4 aspects. First, compare with existing tracking algorithm. This one can significantly improve the performance of a visual tracking system due to its high abundance and high accuracy. Second, the new feather matching algorithm based on the combination of reconstructed model and BDF algorithm is improved and beneficial. Third, the algorithm based on LM iterative can effectively and rapidly convert to minimum reproduction error, improving the performance of the real-time tracking system. Meanwhile, in order to improve system robustness, the ZAC algorithm is applied in the reconstructed model-based real-time tracking algorithm for outlier filtering. In the experiment, shortcomings of this algorithm still exist and should be focused as follows. First, some errors are inevitable resulting from numerical calculation applied in the algorithm, leading to the jitter issue. Second, 2D and 3D matching and LM iterative algorithm run quickly enough. However, 6-point structure runs slowly, which significantly impacts the real-time performance of algorithm. GPU-based extraction algorithm can theoretically accelerate the calculation speed. Third, it is harder to eliminate mismatching points in 2D and 3D matching. Decreasing the number of mismatching points is the only way to avoid such mismatching as much as possible. To sum up, the steps of real-time tracking algorithm based on reconstruction model were established and several conclusions were drawn. The operation speed of the algorithm is mainly determined by 6-point instruction, 3D and 2D and 3D feather matching and LM pose estimation. The experimental results show that the speed of 6-point extraction is relatively slow, while the one of 2D and 3D feather matching and LM pose estimation are fast. The experimental system can establish the 2D and 3D matching quickly and accurately, which ensures the accuracy and stability of the tracking results. Due to the improvements on data points, matching of the algorithm, such as 2D and 3D matching via BDF algorithm and removing mismatches by Ransack algorithm. Additionally, the reproduction error is less than 1 pixel. That is, the accuracy of target tracking is in sub-pixel level. Therefore, the algorithm has almost no error in visual range of human vision. In the following research, fifth algorithm needs to be improved so that the speed of extracting can be lifted. The visual tracking performance of AR on-orbit teleoperation system should be optimized for the further promotion of the human-computer interaction experience in the process of on-orbit teleoperation. Okay, that's all. Thank you for your attention. Thank you.
My name is Wei Wu from Beijing Institute of Spacecraft System Engineering, Beijing, China. Thank you for listening to my presentation on onboard software maintenance design and implementation for networking satellites. My presentation includes 5 parts. First, design motivation, just give you the background of the design and why we should pay attention to networking satellite software maintenance. Second, I will show you the mature single satellite software maintenance design skills and then show you the software maintenance for networking satellites. The fourth part is about the kernel design of the maintenance server. At last, and software maintenance of networking satellites is introduced. With the rapid development of space industry, the types of the functions of satellites are also expanding. While the development cycle of satellites is constantly shortening, in order to adapt to expansion of the complexity of satellite functions and the compression of the development cycle, the satellite function tends to be more and more defined and implemented by software. Therefore, there are more and more embedded software and FPGA items in a satellite. At present, a large satellite has hundreds of software items. The satellite function can also be modified by changing the software code. It has 3 reasons. First, correcting software errors. The second is to adapt to the space operation environment, like single effect upset. Third, software functions upgrading. The design of onboard software maintenance is mostly for single satellite. The design for networking satellites is very few. Here I will give you a short introduction to single satellite software maintenance. Look at the pictures. It gives a basic operation method for software maintenance. The electronic unit has an SRAM-based FPGA that needs to be maintained. The ground system is to cut the configuration data of the FPGA into data blocks continuously and organize them into telecontrol frames. The ground telecontrol system uploads these frames into the satellite one by one. The frames will reach the CMD receiving block of the OBC through transponder and pass and distributed to the maintenance-related electronic unit through the 1553B bus interface. The telecontrol data frames are directly written into the program memory frame by frame without corresponding connection, storage, processing, and distribution. The maintenance efficiency depends on the bottleneck of 3 parts. First, the rate of the telecontrol channel. Second, bus data transmission rate. And third, the rate at which the FPGA control block writes data to the program memory. Now let's talk about the software maintenance for networking satellites. First, we should talk about the characteristics of networking satellites. All satellites operating in a network have exactly the same or similar functions, such as one certain generation of GPS navigation satellites, and all the same software items have the same function. That's the question here. Are all software program data with the same functions on networking satellites consistent? It depends. For FPGA, all the configuration data are the same for different satellites, but for CPU software, some parameters may be different, such as spacecraft identification (SCID). We can deal with this difference by preloading these parameters in non-volatile memory, and then the software configuration data are all the same. So, all the software with the same functions are consistent. This is very important for the next introduction of maintenance method. The networking topology of satellites is usually divided into hybrid network and single network. The maintenance design of networking satellite is to select one satellite as the software maintenance server, which receives the upgrading data from technical control system. For hybrid network satellites, the observation and the control of high orbit satellites has a non-visible time, which is suitable for as software maintenance server. For example, for the satellite networking containing GEO orbiting satellites, GEO satellite is always visible from ground. For a single satellite network, the design and hardware configuration of each satellite are the same, and the visibility from ground is basically the same. So everyone has the same condition as the maintenance server. Now let's talk about some design skills for maintenance server. First, the maintenance server functions are implemented in onboard data handling system. The maintenance starts with a command of maintenance start instruction. When the OBDH system is okay, then the maintenance data will inject it from ground with each frame. Every frame should be CRC checked. If it's correct, it's okay, and if it's not correct, the frame should be retransmitted from ground. The data frame format is generally Virtual Channel Data Unit (VCDU), which adopts the standard CCIDS format. The OBDH system completes the CRC verification of each frame. We can define the parameter non-continuity by the VCDU counter or frame sequence in data section. When there is CRC error or frame loss according to the frame continuity interpretation, the corresponding frame will be re-uploaded from the ground. Then all the frames of data are received correctly. All uploaded maintenance data need to be stored for subsequent writing into memory or distribution to other satellites. Program data can be stored in RAM or flash. RAM is not suitable for long-term storage of maintenance data due to data loss or power failure. After receiving maintenance data, the OBDH system can temporarily cache it in RAM. Flash or EEPROM is suitable for long-term data storage because data in which can be saved even when it is powered down. Therefore, the maintenance data needs to be stored in high-capacity flash or EEPROM after receiving and checking. According to the way of storing data, it can be divided into three ways. The first is to store the whole VCDU frame. The second is to store the VCDU data containing the head. The third is to store only program data. Which one is best? It depends on your design. Everyone is okay, no good, no bad. When receiving the ground command to start the maintenance of a software program on the local satellite, the OBDH system reads the maintenance data from flash and completes the verification, and then reframes the data according to the local data transmission protocol to distribute the data to the destination electronic unit, which completes the receiving, storage, and processing of the maintenance data. The local satellite needs to send the following commands autonomously through the inter-satellite link. Send the maintenance data instruction so that the destination satellite begins to prepare to receive maintenance data. Read out the maintenance data from flash and complete the verification. Reorganize the frame according to the data frame format of the inter-satellite link and send it to the destination satellite frame by frame. The destination satellite will return some telemetry information of the received maintenance frame. The local satellite can reissue the lost frame or wrong frame information according to the telemetry judgment until all data frames are correctly sent to the destination satellite. Send the maintenance data verification command. After the verification is correct, the destination satellite writes the data into the flash to complete the receiving process of maintenance data. According to the data distribution design in the above section, it is necessary to send control instructions from the ground and maintain the software program one by one. The advantage of this updating method is high reliability. The designer confirms the necessity and the feasibility of the software updating. However, the workload of the manual updating will be unbearable when the scale of networking satellites increases to hundreds or thousands. So we should utilize the automatic updating method like the consumer electronic product. It's very high efficient. Then how to make automatic updating for a lot of satellites? The ground injects the software update program as well as version information and the applicable satellites list into the software maintenance server satellite A through the satellite ground link. Satellite A sends the software version information to hand-in-hand satellite B through the inter-satellite link. When satellite B finds that the software version is higher than the current version itself and the applicable satellite list includes satellite B, it sends the software update request to satellite A. After receiving software update request, satellite A will send the software update data to satellite B according to the method in above section. While the updating all data and runs successfully, satellite B will send the updated software version information to the other satellites, like satellite C. There are still two problems. Satellite C receives updating message from satellite A and satellite B at the same time. Satellite C should send updating request to which one? Satellite A or satellite B? Selecting satellite A or satellite B depends on the bandwidth. Well, the bandwidth here is the link available time multiplied by the link rate. Bandwidth is not available for one-time updating. For example, satellite A just sends 50% data to satellite B. Then the link is interrupted. Satellite B should wait to connect with satellite A next time or send updating request to other satellites. Satellite C. Both are okay. Plan A is simple, but maybe take a long time for next connection. On the other hand, plan B is complex. Satellite B should tell satellite C just transmits the late half data. An example for networking satellite software maintenance is given. 2 space routers were used for relevant maintenance tasks in the laboratory. These 2 routers are used for 1 GEO and 1 MEO orbiting satellites respectively. The basic structure of the route for GEO satellite is shown in the figure. The onboard route includes CPU systems, FPGA system, and solid-state storage system. The CPU system includes processor, program memory (PROM), and data memory (SDRAM). And the interface with the FPGA system and storage system is I/O bus. The FPGA system includes Vertex FPGA, controlling ASIC circuit, and FPGA memory, a program memory, NOR flash. According to one link state of the satellite in orbit, GEO satellite high-speed port 1 is connected with MEO satellite high-speed port 1 by cable, indicating that the 2 satellites are linked in orbit. In the initial state, the Vertex FPGA version number of both routers is 0, and then the program of GEO satellite router Vertex FPGA is updated to version 1. At the same time, the configuration data are stored in the solid-state memory NAND flash. The version information is transmitted to the MEO satellite space router through the inter-satellite link. When the MEO system finds that the program version of Vertex FPGA is lower than the FPGA program version of the GEO satellite, it immediately initiates an update application. After GEO orbiting satellite receives the request, its CPU software reads out the configuration data of version 1 in the solid-state memory into SDRAM and completes the verification. Then it is raised, split, and packaged to form maintenance data frame to send to MEO satellites according to the inter-satellite link data frame format between the 2 satellites. The MEO satellite stored all the configuration data in the SDRAM when it receives the maintenance data through one inter-satellite port 1. After the data frames are connected completely, all the configuration data are written into program memory NOR flash of FPGA. Okay, conclusion. One method for networking satellites is present. Automatic updating is important for hundreds of satellite software maintenance. Automatic updating is achieved by exchanging version and applicable satellite lists between adjacent satellites. Thank you for your attention and patience. Thank you for your listening again. Any questions?
My name is Dong Hui. I'm from Institute of Spacecraft System Engineering, Beijing, China. The title of my academic presentation is Model-Based Development of Spacecraft Orbital Software. My presentation will include those 5 parts. Part 1 is the introduction. Part 2 is the design idea. Part 3 is the development process. Part 4 is the simulation verification. And Part 5 is the conclusions. Part 1, the introduction. In the traditional software development process, the design results of each stage are presented in the form of documents and transferred between stages, thus forming the document-based software development mode. However, with the increasing complexity of spacecraft software, the traditional document-based software development mode is facing more and more obvious difficulties, including backward representation, lack of early verification means, and difficulty in reuse. For the above reasons, model-driven software development has gradually attracted attention in recent years. Model-based development takes models as the core of software development and guides software understanding, design, construction, development, operation, maintenance, and modification. Model-driven development also makes the information transfer between each stage of software development process from the past documents to models. Part 2, design idea. The functions of the orbital subsystem software, including managing the whole satellite bus network, telemetry, remote control, program control, and satellite management. The software is generally a multiprocess software based on the real-time operating system. There are 2 goals for the development of model-driven orbital software. First is to build a universal software architecture model and model the main business requirements. At the same time, the trusted model library is accumulated on the basis of software components to form organizational assets. The second goal is to find a model-based software development process suitable for spacecraft orbital software and build a prototype system. And objectively evaluate the impact of model-based software development on the development efficiency and quality. The overall design idea is divided into the following 4 parts. Each research content is progressively in order. The above research content is used as input, and the results are provided to the next research content, thus forming a research process of progressively and clear research purpose. The first stage is general functional requirement modeling. The goal is to quickly determine the logic and the basic functions of the requirement object, establish the connection between the requirement and the model, and do not need to go deep into the internal detail of the model. At this stage, it is required to quickly verify whether the data interface input and output between the requirements and the complete system are reasonable, and determine the main business functions. The second stage is model architecture design. We develop a universal OBDH software architecture model that includes telemetry, remote control, bus communication management, satellite time management, memory read, and other functions common to the spacecraft OBDH software. Based on the actual project needs and the technical characteristic of OBDH software, the research has built three different forms of software architecture model. One is the general software architecture model, in which common software can be integrated. The architecture has complete functions and the model is simulated and verified. The other is the general software architecture model and the self-developed general test software are connected through TCP/IP network, supporting the telemetry downlink and receive remote control commands, and supporting bus data simulation. The other is the general software architecture model, and the underlying driver and operating system interface are jointly compiled through makefile, and then the binary executable file can be directly downloaded to the hardware device or to simulation test software for running. The third stage is functional model encapsulation and model library construction. Model library organizes many function models according to fixed structure and effectively manages and uses each functional model through a unified model-based management system. From the perspective of software, each functional model in the model library is a model architecture that can be reused and assembled into an application system. The last stage is automatic generation of software code. After building the software model, code generation is carried out. At the same time, combined with a compiler set by the user, the target file can be compiled to generate an executable file. Part 3 is a model-based development process. First, we use the requirement editor to sort and decompose the requirement. Then use System Composer to model the software requirement and establish the link between the requirement and the model. The correspondence between the requirement model and the design model can be realized by dragging the requirements items directly, and the completeness of the requirement realization can be verified. The finger shows the requirement model framework design and interface design. The universal software function model architecture of OBDH is implemented by using Stateflow Toolbox Simulink model library and MATLAB M function. This research only models and generates code for the application layer of the OBJ software and conducts some special processing and integration for the underlying hardware driver and the interface between the application software and the operating system. In addition, considering that spacecraft orbiter software has generally established an organizational assert library of software components. This part of code can be directly integrated into the entire software model without modeling and code generation. This figure shows the overall architecture of OBJ model. Model-driven software development needs to establish code generation configuration items according to the requirements of code generation. In this research, two different configuration sets are established, namely the configuration set for simulation and the configuration set for code generation, so that the functions of model simulation and code generation are realized in a set of models. Users can browse and modify the content of those two configuration sets through the Model Explorer tool. After the simulation and verification of the OBDH software model is completed, C code can be generated. The generated C code can reveal the generated report and track the relationship with model, as shown in the figure. Finally, compile the automatically generated code and handwritten code, and download them to the hardware environment or virtual software testing environment for running. Part 4 is the simulation and verification. The spacecraft OBDH software model is based on Simulink standard model development environment. Through the intermediate communication mode, the interface between the spacecraft OBDH software mode and the traditional ground test software is connected. Based on the existing mature ground test software, the rapid verification of the mode in the loop and hardware in the loop of the spacecraft orbital software mode is realized, and the entire mode-based development process is fully connected. The environment of the spacecraft OBDH software based on this method is shown in this figure. The mode test environment is built, and the mode closed-loop simulation test is carried out, and the consistency between the automatically generated code and the running result of the mode is verified. The technical indicators achieved in this study are shown in this table, including functional items covered by the mode, automatically generated code, and the exclusion efficiency of automatically generated code. And the last one is the conclusion. This research changed the development mode of spacecraft orbital software from the traditional handwritten to model-driven, and verified various technologies such as software requirement modeling, general architecture model, general model library, and model simulation and verification, and software generation. By connecting the existing general software test platform with the model, the efficiency of model simulation verification is improved. That's all. Thank you. My name is Dong Hui. I'm from Institute of Spacecraft System Engineering, Beijing, China. The title on my academic presentation is Design of Aerospace Cloud Computing Server based on Docker Cluster. My presentation will include those 5 parts. Part 1 is the introduction. Part 2 will introduce container technology and cloud-native architecture. Part 3 is the design of our space-based cloud computing server. Part 4 is the instant verification, and Part 5 is conclusions. After years of construction and development, although the ground-based information acquisition, transmission, processing, and application systems with professional application as the main goal have been initially built, those systems are distributed in different regions, belong to different management departments, and have different development platforms, and lack of unified specifications, forming a pattern of chimney development, resulting in low efficiency of resource use, difficulties in information sharing, poor timeliness and of task response. It restricts the full play of the resource efficiency of the entire space-based information system. With the continuous deepening of the space-based network demonstration, the space-based network information system with the ability of supercomputing, fast storage, massive transmission, and flexible reconstruction is a core system that needs technical breakthrough. Cloud computing system provides a strong technology support for improving the server capability of information system. In cloud computing, software and hardware are virtualized into logical resources. No matter what kind of device the terminal is, it can access services on demand through the network without paying attention to its internal structure and operating mode. The emergence of cloud computing technology provides a new idea for the implementation of information services. Part 3 is about container technology and cloud-native architecture. Virtualization refers to simulating physical hardware resources into multiple logical devices through software. and programs can run on independent logical devices without affecting each other. In virtualization technology, Docker plays an important role as an open source container energy. Compared with traditional virtual machines, Docker containers are relatively lightweight. Docker daemons can directly communicate with the main control system, local resources to containers, and isolate containers from the main system and containers from each other. Cloud-native technology is a collection of a series of technologies, including containers, container management, microservices, DevOps, and intelligent operating and maintenance technologies, among which containers are the core technology of cloud-native infrastructure. Cloud-native is designed to deploy to the cloud. To ensure the successful operation of container applications, the operating system needs to support relevant services. Cloud-native widely adopt the Docker and Kubernetes technology architecture. Users can create application images based on it and run them directly on the cloud. The physical hardware resources are simulated as multiple logical devices through container virtualization technology, and the program can run on independent logical devices without influence, thus providing a lightweight isolation environment for software development, deployment, and operating. Part 3 is the design of space-based cloud computing server. In order to achieve high-speed transmission, intelligent processing, mass storage, and other space-based distributed cloud information services, the space-based cloud computing server is designed based on the Space VPX standard. Based on the standard, the hardware modules with different functions are assembled to form a combined application product. The hardware modules are connected through backplane buses at different levels, so as to achieve a high degree of flexibility and scalability in the information interaction between the modules in the whole machine. The prototype of the space-based cloud server is internally integrated with high-performance computing module, high-capability storage module, and routing switching module, realizing the integration of computing, storage, and network resources. The layered design of the Docker-based cloud server system is shown in this figure. It consists of 5 elements, including high-performance computing module, customized highlight onboard operating system, container cluster management middleware, container application, and range monitoring system. After integrating the virtualization container technology on the customer's lightweight operating system and releasing the application server containerization, the container application can be scheduled and deployed through the container cluster management middleware, so as to achieve the resource virtualization and balance scheduling on multiple physical computing units in the satellite. Provides a unified standard virtual operating environment for various users and applications, and achieve on-demand resource allocation and elastic computing. The traditional embedded real-time operating system, such as VxWorks and Atoms, are not completely suitable for the application scenarios of space-based cloud system service after being customized. The reason is that space-based cloud server requires the operating system to support virtualization, cloud-native AI, and other technology, in addition to the high real-time requirements of the operating system. However, the early embedded real-time operating system in the aerospace field have limited functions and poor software ecologies. At present, Linux operating system is widely used in cloud computing service on the ground. Although it's not a hard real-time operating system, the real-time performance can be greatly improved to microseconds by inserting RT-patch into the Linux kernel, which can meet the requirements on real-time processing on the satellite. K3s is a lightweight cloud-native framework based on Kubernetes. A single node can be selected as the single-node architecture of the server-side. The K3s cluster of the single-node architecture can meet all the task requirements. The architecture is shown in this figure. In the single-node architecture, the cluster has only one K3s server node and embedded secret database. Each agent node is registered to the same server node. The administrator of the K3s cluster can directly allocate all node resources in the cluster through the cluster API functions on the K3s server node. Deploying K3s in the onboard computer environment can facilitate the management of container application on multiple computing styles to achieve load balance and resource integration among computing styles, thus further realizing multiple style computing. In addition, K3s can realize the migration of cluster content application so as to ensure the reliable operating of applications in the K3s cluster. Part 4 is the instance verification. On the prototype of the space-based cloud server, the K3s based container cluster management is verified by an example. In order to facilitate the deployment and management of containers, the container management platform Rancher is installed on the space-based cloud server. The Rancher server can be deployed in one of the high-performance computing models. The ground-based monitoring terminal can monitor the health state and capacity of the container cluster through the browser and perform elastic resource allocation. 3 high-performance computing models are deployed in the prototype computer. One of them is selected as the server node of K3s, and the other 2 are selected as agent nodes. We call it agent 1 and agent 2 respectively. The Rancher server is deployed on the server node. This figure shows the dynamic migration management of container application in cloud computing server. In the case test process, after the initial deployment of 10 container applications, the 3 nodes run multiple container applications according to equilibrium strategy. The Agent 2 node was manually isolated from the system. The container applications originally run on the Agent 2 node were automatically merged to the server node and Agent 1 node. After the Agent 2 node is rejoined to the system, after deleting multiple container applications from the server node and agent node, some of the deleted container applications will be automatically migrated and deployed to agent 2 node according to the load balance policy. The conclusion: running on the application software on the onboard computing in the form of a container can not only solve the capability problem during software deployment, but also improve the security of onboard applications through the resource isolation between containers. At the same time, the container cluster management method is used to deploy satellite applications on multiple computing cells. The container application can be deployed on multiple computing cells with one click only once. After the application of container technology, the deployment and the maintenance efficiency of onboard software will be greatly improved. That's all. Thank you.
My report is research and application of energy efficiency optimization algorithm for spacecraft simulation platform. 1. Introduction. High-performance computing plays an increasingly important role in the simulation and verification of the aerospace field. In the aerodynamic prediction and verification of Tianwen-1, the specific experiments of aerodynamics and aerodynamics were carried out in the Martian atmosphere during the Mars entry, descent, and landing mission. In the Chang'e 5 mission, an expected mission option schedule was designed for the orbiter, and the trajectory design dynamics model simulation was carried out to maximize the use of mission resource. In the new generation manned spacecraft, the airbag finite element model is established to simulate the landing buffer process of the return capsule, effectively reducing the possibility of hard landing. With the increasing size and quality of spacecraft, all kinds of simulation tasks tend to be complex and require high solving time, which put forward high requirements for the computing capability of the platform, while improving the computing power of the platform. Its performance and size are growing year by year, and its energy consumption is also growing significantly. How to improve the energy efficiency rate of the data center? The answer is to balance the energy consumption and the performance of the platform. In the high-performance computing data center, the energy consumption of IT equipment mainly comes from the operation of jobs on the computing nodes. For servers without computing tasks in idle state, a large amount of energy consumption is wasted. How to optimize the job scheduling strategy on the promise of ensuring the platform throughput and computing efficiency is of great significance to improve the energy efficiency of the platform. In this paper, by analyzing the computing characteristic of spacecraft simulation tasks, modeling the platform operation distribution, resource utilization, and energy consumption, then propose a scheduling algorithm based on energy efficiency optimization, which effectively reduces the platform energy consumption and carbon emissions. 2. Related work. The data center energy efficiency standard commonly used in the industry is mainly power usage effectiveness, PUE, the rate of the total energy consumption of a data center to the total energy consumption of the IT equipment is used to measure the effective energy consumption of the data center. Technologies for energy consumption optimization of IT equipment include dynamic voltage and frequency scaling and dynamic power management. It is based on the integer linear equation of power configuration, proposed a scheduling strategy using DVFS to dynamically adjust the power consumption of computing nodes to control the power consumption of the entire platform. Yang proposed a cloud infrastructure. It through the integrated management of various resources and the distribution self-organization mechanism based on game theory, making decisions on dynamic resource costs with less delay so as to reduce the operation power consumption. The energy consumption of the data center mainly comes from the operating load of IT equipment and the operating consumption of refrigeration equipment. 15% to 30% of servers in IT equipment are idle, and the energy consumption in idle state accounts for 15% to 16% of the full load energy consumption. The server runs with the highest energy efficiency under full load, and the energy efficiency drops sharply when the load decreases. For the common server utilization rate of 20% to 30%, its energy efficiency is less than 50%. 3. Energy consumption model analysis. In the spacecraft simulation computing platform, computing nodes account for more than 90% of IT equipment. This paper mainly focuses on how to improve the energy efficiency rate of computing nodes, thereby reducing the overall energy consumption of the platform. Due to the large scale of calculation model, the computing capacity of the platform is required to be high. At the same time, the model task has certain periodicity, which leads to the platform resources cannot be fully utilized in real time. When the platform resources can't be used 100%, some computing nodes are idle, resulting in waste of energy consumption. The total time of platform resources is below. The Ti idle represents the time when the node I is idle, and the Ti busy represents the time when the node I is busy. The platform resource utilization rate is the rate of the sum of nodes running calculation jobs to all resources of the platform. If no energy-saving measures are taken, all nodes in idle state are in running state. The platform power consumption is below. The Ei idle represents the power consumption when the node I is idle, and the Ei busy represents the power consumption when the node I is busy. How to reduce the use of computing nodes and improve the utilization of a single computing node, without job scheduling and running time be affected. 4. Algorithm design and implementation. Resource management and scheduling are the core components of high-performance computing platform. A scheduling algorithm based on energy efficiency optimization is designed. Through reasonable resource scheduling and allocation, the power consumption of computing nodes is reduced while avoiding frequent node state transition, ensuring platform throughput and efficient operation of jobs. The computing nodes, node 1 to node I. The logical partitions, P1 to Pj. It is used to locally isolate computing nodes. The scheduling algorithm based on energy efficiency optimization mainly focuses on the resource scheduling level of partition computing nodes. First, the computing nodes in the partition are numbered. In the process of job scheduling, the computing nodes with the highest number are performed, then initialize the computing nodes in the partition. All nodes are set to the running state and can receive jobs. The strategy can be used in combination with traditional scheduling strategy. First, the platform can receive submitted jobs in real time. Second, according to certain strategy, it selects the first node in the partition that meets resource requirements to the selected job. This can effectively improve the utilization of computing nodes and optimize the energy efficiency of every single computing node. In the process of resource scheduling, it is necessary to uniformly manage resource state switching, dynamically configure switching opportunities and conditions. It combines maintenance with scheduling strategies and energy consumption management requirements. 5. Simulation experiment and analysis. On the spacecraft simulation computing platform, we submit job for experiment verification. The platform architecture is shown in the figure. The platform uses Slurm as a resource management and scheduling tool. Scheduling strategy use first come, first service. Computing nodes are composed of 20 blood servers. Computing network are connected by the IP switches. Data collection uses out-of-band monitoring and in-band monitoring. The out-of-band monitoring uses intelligent platform management interface, and the in-band monitoring is based on an open source monitoring tool, Nagels. Job selection. From the structure, fluid heat, electromagic, simulation calculation. Select a typical application example to build a real simulation job sequence. Platform loading setting. In order to comprehensively analyze the energy consumption comparison of the optimization algorithm in the platform simulation environment. Different platform loads are controlled by the number of jobs. Job scheduling strategy. A comparative test of FCFS scheduling strategy and the scheduling strategy based on energy efficiency optimization. Statistical analysis is conducted for the empty load and the load of 30%, 60%, and 90% respectively, lasting for 13 hours. Under the condition that the running jobs are consistent, the scheduling algorithm based on energy efficiency optimization is compared with the FCFS scheduling algorithm. The total power consumption is counted under different platform load. 6. Conclusion. This paper analyzes the characteristic of spacecraft simulation based on spacecraft simulation computing platform, collecting the actual operation data and analysis the platform energy consumption model on the promise of not affecting the platform's throughput and operation time. Compare the optimized scheduling algorithm with the conventional scheduling algorithm. The overall energy consumption of the platform is reduced by an average of 25%. The algorithm effective improving the energy efficiency and reducing the cost. Later, we can further analyze simulation computing tasks based on historical job operation data, develop timing analysis and prediction based on machine learning algorithm to make it more energy efficiency.
Hello everyone. Now let me introduce my paper, SADA, SDN architecture-based secure dynamic access scheme for satellite network. The presentation includes 4 parts. 1. Introduction. As we know, the characteristic of satellite network is wide coverage, no influence of natural conditions on the ground, and simple and flexible access. It is considered to be an important part of the next generation Internet by many researchers and also a space infrastructure to be actively developed and constructed. But the current access and application mode has some problems. It is difficult to provide more secure, efficient access methods and better service quality assurance with fixed and inflexible manner. They greatly increase the complexity of ground planning with the continuous increase of access users. With the development of satellite network, the application types of access nodes are more abundant and the QoS requirements are becoming higher. So the current access method is unsuitable. In order to solve these problems, this paper proposed a scheme architecture-based secure dynamic access scheme for satellite network, which can authenticate the security of network access nodes and avoid the impact of network performance due to the overload of management nodes in the network. 2. SADA. The SDN-based secure dynamic access architecture is shown below. SADA reputation model makes use of BRSN reputation method and improves the specific application environment of satellite networks. The calculation process of reputation is shown as below. The calculation of reputation value takes the historical behavior of the node as an important measurement element and takes the time period of each access to the network as the calculation cycle. When calculating the reputation of this cycle, the reputation of the first two cycles needs to be considered. One, if has malicious behaviors before all access for the first time, when calculating the reputation value of this cycle, the control change amount is reduced to punish. 2. If no any malicious behaviors before, some amount can be additionally rewarded when calculating the reputation value of the current cycle. In this paper, a node load aware dynamic access mechanism is designed, which focuses on the real-time load state of the satellite, while improving the utilization efficiency of satellite resources. During the access process, the dynamic access selection is made by evaluating the current load state of the backbone nodes, so as to avoid the excessive load of the satellite network nodes and ensure the secure and stable operation of the satellite network. SADA defines a multi-metric parameters dynamic access mechanism and selects the node CPU utilization rate, the signal-to-noise ratio, and the connection service time as the access metric parameters for dynamic access processing, which can be placed with the application scenario. When an access node wants to join the network, the backbone node makes dynamic access selection according to its current performance and connection status with the access node. The resource-aware dynamic access mechanism is shown as below. The satellite network secure dynamic access process is divided into two stages. When the slave controller nodes receive the access request of the data plane node, SADA confirms the reputation of the access node. SADA judges the current access resource status of the backbone node according to the resource-aware dynamic access mechanism and calculates the access probability to perform network dynamic access. Three, performance evaluation. The experiment goal. The end-to-end transmission success rate of satellite nodes is one of the most important network performance indicators, which can reflect the rationality of network architecture, access and transmission strategy, and QoS guarantee capability. We compare the performance of end-to-end transmission success rate of satellite nodes with DQA. The experiment topology in this section is composed of 3 GEO satellites and 66 LEO satellites. The LEO satellites consist of 6 orbital planes, 11 satellites in each orbital plane. On the basis of this topology, 3 to 5 access nodes are set as malicious nodes, and the destination nodes are randomly selected. In order to ensure the authenticity and effectiveness of the test, 100 tests are conducted for each test condition, and the average value is taken to finally obtain the data transmission success rate under this condition. The experiment result shows as the figures. The figures shows the data transmission success rate returned by SADA and DQA respectively. SADA plays better than DQA. Four, conclusion. SADA is a secure dynamic access mechanism of satellite network based on SDN architecture. SDN architecture is adopted to separate the data plane from the control plane, effectively improving the operation efficiency of the network system. Reputation evaluation comprehensively evaluates the current and historical network reputation behavior of a node, which can ensure the security of the network. The mechanism of resource-aware dynamic access selects typical performance and conducts dynamic probabilistic network access, which can avoid overload of network nodes and improve network QoS guarantee capability. Finally, the simulation results show that SADA has a better performance in data transmission success rate. Okay, that's all. Thank you very much.